Alright, so what I'm going to do is I'm going to do an introduction to acid-base pH calculations. You guys did this last year in honors chemistry, so it should be a review. I just want to simplify and hone in on a few concepts. So we're talking about acid-base calculations. So here we go. So when we talk about acid-base and pH calculations, we already talked about what an acid and a base was. One of the things is you have to be able to do in AP chemistry is calculate the pH of a strong acid. How do you know a strong acid? You have to memorize the 6 strong acids, so you should know them as soon as you see them. Very easy calculation. In fact, it's quite simple. All you do is you just take the negative log of H3O plus from the problem. Why? Well, because it's a strong acid, we know it's completely broken apart. So we know that when we have the molarity value for it, we automatically have the H3O plus. So if we're given the H3O plus, if you think back to pH land, here's pH land. If I'm given the H3O plus, it's a simple negative log and I get pH. That's what I have to be able to do, right? Well, so on a strong acid problem, it's very simple. If you notice, HNO3 is a strong acid. I have 0.1 molar NaHNO3, which means since we know it breaks apart completely, that means I end up with 0.1 of this and 0.1 of that. And since I have the H3O plus or the H plus, all I do is just take the negative log of 0.1 and I end up with a pH of 1.0. That's my pH. So when we realize it's a strong acid, it's a very simple calculation, just the negative log. Then we get to the one that occurs more often, weak acid calculation. So when we're talking about a weak acid calculation, what are we dealing with? Well, first of all, it is a weak acid because it's not one of the 6 strong acids that you're supposed to memorize. You have to solve for the concentration of H3O plus because it does not break apart completely. Our fundamental definition of a weak acid, we say that it basically breaks up less than 5%. Because of that, you have to use an ice table in order to find it, but then I'll show you a shortcut. You're going to be given, if it's an acid problem, you'll be given a Ka. If it's a base problem, you'll be given a Kb. Acid and base problems are done exactly the same, except they have Ka values and Kb values depending on which one you have. Now, you'll either be given a K value in the problem, or if you're doing a homework assignment, in the appendix there's a table in the back of the book. So if you look here, here's an example of a Ka or a Kb. So these are acids. So we're talking about acids. So like hydrofluoric acid, for example, has a Ka value of 6.6 times 10 to the negative 4th. So there's a table in the back of your book, or in the chapter that we're doing, you can always look it up if it's not provided, or it's a homework problem from the back of the book. If it's on the AP exam, they're going to give you the Ka value. Bases, so we have bases here. Ammonia is a real famous base. Its Kb value, because it's a base, the subscript is B, 1.8 times 10 to the negative 5th. So when we come back over here, you're going to use an ice table to solve for it, AP style. What does that mean? When you go to do this on the AP exam, you definitely have to show an ice table. I'm going to show you how to do it ice table style, but then I'll show you the shortcut which you can use in my class. We're going to use something called the assumption rule. Because weak acids break up into small amounts or less than 5%, we're allowed to toss out the bottom x, which prevents us, since it's going to be very small, prevents us from having to use the quadratic equation. So in this chapter, there is no quadratic. You don't have to be concerned with it because we're allowed to ditch the bottom x. So keep that in mind. That's important. Because the acid ionizes very little, we can automatically toss out the bottom number, and it works the same way on the AP exam. Since ice tables are, since ice tables are filled in the same, you may go right to the shortcut except on the AP exam. So since they're exactly the same, you always get the same result on an ice table, simply because at that point, 1H is always transferred in all these reactions, so the coefficients are always going to be 1 and 1. I'll show you. Here's an example of a weak acid problem. We have to find the pH. Well, the problem is that 0.15, we can't just take the negative log of it because HF is a weak acid, so that does not work. So the first thing we have to do is write out a weak acid expression. So I write out HF. HF is going to react with water, H2O, because all these things are basically going to be dropped into water. And Bronsted-Lowry acid gives an H, so it's going to deliver an H over here and give me H3O plus F minus. That's my equation for the top of the ice table. Then I'm going to go I, C, E. Well, my initial value, I'll always be provided with an initial value, is going to be 0.15. This is going to be 0 and 0. And the reactions in this case always go forward. Since we don't care about liquids and solids in equilibrium expression, we are allowed to ignore the water. The water plays no role in this. So, since we know this is an acid-base reaction, they're always going forward, always to the right. This makes this minus x plus x plus x. When I drop everything down, I get 0.15 minus x, x, and x. That's my E line. Now, when I go to put this in expression, if you think about it like this, when I go to put this into an expression, it would be Ka is equal to the concentration of H3O plus to the first and F minus to the first over HA, or HF, sorry, HF. HF. Now, these don't have exponents because, again, going back to a weak acid reaction, you're only transferring a single H every time. So since this is only transferring a single H, the coefficient here will be 1 and here will always be 1. So you're ultimately always going to end up with X and X on the top. And then this will be my bottom, and water is ignored. So my ultimate expression is going to be H3O plus times F minus to the first divided by HF. Well, if I go back to the E line, I'm going to grab my top values, X and X. That means I'm always going to end up with X squared on the top, because I'm going to always have plus X and plus X. Then I go to the bottom, and I grab my bottom piece, which is 0.15 minus X, and we know it's equal to Ka, so I'm going to take the Ka, which is 6.6 times 10 to the negative fourth. Now, remember I was talking on the previous slide about the assumption rule? Because we don't want to get into the quadratic equation, what we're allowed to do in chemistry and on the AP exam, we assume, it's called the assumption rule, we assume that value is so small it doesn't really have too much impact on our calculations. So we delete the bottom X, which then leaves us with that. So then the next step is to algebraically solve for our value. So when you solve for X after you do it and you punch in your calculator, you end up with 0.0099. That's X. If I come back and look over at my ice table, the thing that I need to find pH is H3O plus. So now I have my value of H3O plus because I just solved for it on my ice table. So that's how I'm going to find pH. Because if I go back to pH land, here's pH land right here. If I go back to pH land, I now have 0.0099 because I was dealing with an acid. Now I have my H3O plus. If I take the negative log of that, I get a pH of 2.00. And that's how I find the pH of a weak acid. I find H3O plus, but via an ice table. So if I look, let's take a look at the next problem. What is the pH of a 0.025 molar solution of benzoic acid? They give me the Ka. I'm going to use the generic form of a weak acid. Instead of writing out the whole formula, I can just write HA, represents the acid. It's going to react with water. Double arrow, I'm going to get H3O plus A minus. Then I'm going to do my ice table. This is the last time you'll see me do an ice table. Well, not the last time, but 0.025 goes in here. Don't care about water. This is automatically going to be 0 and 0. I know it's going to go to the right. Minus X plus X, oh surprise, plus X, sounds familiar. 0.025 minus X, X, and X. Ultimately, what do I end up with? X squared over 0.025 minus X, and my Ka value is 6.3 times 10 to the negative fifth. Remember, I get to use the assumption rule. So automatically, I'm going to delete the X on the bottom, and then I'm going to use a little algebra. When I solve for X, I get 0.0013. So my X, remember when I solve using a weak acid, the thing I'm really trying to find in order to be able to solve pH is H3O plus. I just found it. So then if we go to pH land, I have 0.0013. I punch that into my handy dandy calculator. I take the log, negative log of it, and I get a pH of 2.89. Bam! Boom shakalaka. So ultimately, when you have a problem that you recognize as a weak acid problem, I know I'm going to end up with this. X squared over molarity minus X is equal to Ka. And we're always allowed to throw out the X, so ultimately our acid-base shortcut is X squared over molarity is equal to Ka, basically. That is our shortcut. Now, since we know there's a Ka here, that means our X is equal to H3O plus. Always, we have to keep that in mind. So like if you have a problem here, they tell us the molarity of the acid, so I have that value on the bottom. But wait, they're not giving me the Ka this time. They want me to solve for the Ka. So I don't know what the Ka is, but I need the other X value. This is where you have to think as a chemistry student. They will always provide you with 2 out of the 3 values in a weak acid problem. If you notice right there, technically they're telling me what X is. Where does that come from? Well, if you go back to pH land, and you have to be aware of it, if I have a pH of 5, I think it was 5.35, technically, I can convert that into H3O plus. So you have to know whatever values they give you in pH. They could give you pH, POH, OH, H3O plus. You have to basically ultimately get and find out whatever value it is you need. In this case, I need H3O plus because they're having me solve for the Ka at this time. So I need this value right here. So then the opposite of pH, if I look at it, is 10 to the negative pH. So what I would do is take 10 to the negative 5.35, and I get 4.5 times 10 to the negative 6 is my value for H3O plus by converting pH to H3O plus. So then that means my X is 4.5 times 10 to the negative 6. So I go back to my expression here. So I'm going to go 4.5 times 10 to the negative 6 goes here. I'm going to square it. My molarity is already given to me, 0.15. So then if I plug this into my calculator, I am able to calculate out the Ka value. I square the top, divide by the bottom, and ultimately you end up with 1.4 times 10 to the negative 10th, I believe, when you calculate it out. Now, the weak acid shortcut, just so you know, when you go to do a weak acid problem, it's going to be X squared over molarity equals Ka. If this is Ka, it means my X is H3O plus. You have to be aware of that problem solving, just like the last problem where they asked me to solve for Ka. So to find the pH using the weak acid process, you need 2 out of the 3 variables, molarity, Ka, or H3O plus is assigned to you, 2 out of the 3, and then you solve for whatever you need to. Usually you're going to solve for H3O plus, which then allows us to take the negative log of it, and then you find pH. The negative log of H3O plus will get you pH. One last thing before I go is they will ask you a lot of times to calculate out the percent dissociation. Since these acids don't completely break apart, you can calculate out its percentage. The original molarity you're given times when you solve for X over 100 will tell you how much percent is dissociated. Here's an example. If we look at this problem right here, the original pH was 0.025. So if I take 0.025 is my molarity, because it's molarity on the bottom, and then my X. My X came out to be 0.0013. So I put 0.0013 on the top times 100. So when I do it on my calculator, I get 0.0013 divided by 0.025 equals, and then I multiply times 100. I end up with 5.2%. That tells me how much dissociated or how much the weak acid broke up. We know the weak acid barely breaks up, so 95% of this thing stays together. Only 5% of it breaks up into H3O plus. So it's a quick thing that they ask you a lot of times on the exam to do. Percent dissociation is simply the original molarity divided by the original or the X amount, the H3O plus that you solve for. The original molarity of the acid just times 100 will get you percent dissociation. Have a good weekend and go Broncos. Woo!